In this brief chapter, we will be looking at acids and bases. First, we'll take a quick look at Arrhenius acids and bases. This was developed in the 1880s. Bronsted-Lowry acids and bases and Lewis acids and bases were both developed in 1923, and they differ in terms of perspective because the Bronsted-Lowry focuses on the proton, whereas Lewis focuses on the electron. According to the Arrhenius definition of acids and bases, an acid is something that produces H plus in water, and a base is something that produces OH minus in water. As an example, we could think about HCl and NaOH. When HCl is in water, it will dissociate to form H plus and Cl minus. That's one way to think about it. Or we could think of it that when HCl is in water, it will form H3O plus Cl minus. With sodium hydroxide, we can think of sodium hydroxide dissociating to form sodium plus and hydroxide. Or we could think of it as sodium hydroxide plus water will give sodium ion plus hydroxide plus water. When we have an acid reacting with a base, they are going to form water and, in this case, sodium chloride, which is a salt, and so this is called a neutralization reaction. So this might be the definition that you saw maybe in high school, possibly it was mentioned in general chemistry, but the problem for us as organic chemists is that these definitions are based in water, and there's a lot of chemistry that doesn't happen in aqueous solutions. So for the most part, we are going to ignore this. I wanted to mention it just to be able to make a connection if this is something that you heard before, but we're going to focus on the Bronsted-Lowry definitions. So, according to the Bronsted-Lowry definitions, an acid is a proton donor and a base is a proton acceptor. Now, wait a minute. I said proton, but I wrote H+. So what am I talking about? Well, keep in mind a hydrogen atom has one electron and one proton. So if we are talking about a hydrogen ion, if we're talking about H+, that means that we lost one electron, and so all we have is a proton. So H+ is interchangeable with a proton. Now here we have an example of an acid-base reaction where we have HCl reacting with NH3 ammonia, and these will react to give chloride plus ammonium ion. Well, let's look at this in more detail. If we have HCl and we have ammonia, these can react together. Ammonia can act as a base and it can grab a proton, allowing these electrons to fall back onto the chlorine. So that means that on the nitrogen, what used to be a lone pair on the nitrogen is now used to form a covalent bond between the nitrogen and the hydrogen, and this gives nitrogen a formal charge of +1. And then chlorine still has its 3 pairs of electrons, and now it has one more pair, which gives it a formal charge of -1. Notice we have a formal charge of +1 and a formal charge of -1, so on the right side our total formal charge adds up to 0, which is the same as what we have on the left. So in this example, we can see that ammonia is the base because it grabs the proton or it accepts the proton, and then HCl is the acid because it donates the proton. the proton is grabbed off of HCl. So according to the Bronsted-Lowry definition, an acid-base reaction is a proton transfer. Even though we talk about it as a proton transfer, we have to remember that a proton can't just hop off of an acid and go over to a base, because all reactions are driven by electrons. Rather than thinking about a proton donor or proton acceptor, as I'm talking about an acid-base reaction, I say that the base grabs a proton from the acid because the reaction is driven by the electrons. As we're thinking about Bronsted-Lowry acids, how can we compare acid strength? Well, acid strength is defined by the reaction in water. So defined by the reaction of an acid, let's say generic acid HA, in water. So if we have our HA and this reacts in water, this will be our acid and water will act as our base, giving us H3O plus plus A minus. So this is our conjugate acid, and this is our conjugate base. Because if we're thinking about the reaction in the reverse direction, this is the one that loses a proton to become water. This is the one that gains a proton to become HA. Now, in general chemistry, you probably spent a lot of time talking about equilibrium expressions. So we're talking about reactions that move in the forward and the reverse direction. And in general, for the equilibrium expression, we have the equilibrium constant, which is a capital K, and that is equal to the concentration of products divided by the concentration of reactants. So in this case, we're looking at the acid dissociation constant, which is the equilibrium constant for this acid dissociation reaction. So in this case, Ka is equal to the concentration of products, which would be concentration of H3O plus times the concentration of A minus divided by the concentration of reactants, which would be HA. We don't include water as one of our reactants because it is the solvent. And so we ignore the solvent because it would be a constant, so it's taken into consideration in the equilibrium constant. So this is how the acid dissociation constant is defined. Now, let's say we are talking about a strong acid. One way to think about that is that HA plus water is going to react very far to the right to give H3O plus and A minus. And in this case, the equilibrium lies very far to the right. So as we think about the equilibrium expression, then our Ka, where we have concentration of H3O plus times the concentration of A minus divided by the concentration of HA, well, because the equilibrium lies to the right, that means we have lots of product, and so the numerator is going to be really big. We have a little bit of reactant, so our denominator is going to be small. So overall, that means that our Ka is going to be a big number. On the other hand, if we have a weaker acid, we're still thinking about HA plus water, but in this case, our equilibrium lies to the left. Our products are still H3O plus and A minus. But now, when we look at our Ka, concentration of H3O plus times the concentration of A minus divided by the concentration of HA, because the equilibrium lies to the left, that means we have very little product, and so our numerator is going to be small. and we have lots of reactant, which means our denominator is going to be big. So overall, that is going to give us a small number. So the Ka, the acid dissociation constant, if it's big, that means it's a strong acid. If it's small, that means it's a weak acid. And this is convenient because as long as we have an idea of the overall reaction, there's some intuitiveness about this. So let's continue to think about our Bronsted-Lowry acids, and we're thinking about the acid dissociation reaction and our acid dissociation constant. So the Ka is equal to the concentration of H3O plus times the concentration of A minus divided by the concentration of HA. This makes intuitive sense because if the value is big, that means we have lots of products. If the Ka is small, that means we have very little products, lots of reactants. So that's good. It kind of makes sense. But the problem is that in some cases, we might have a Ka that is like 1,000,000. Or we could have a Ka that is really, really, really small. So good news, intuitive; bad news, really big or really small numbers, which means we might have to use exponents and scientific notation, and that just gets difficult to work with. So rather than sticking with Ka, instead, chemists use the pKa. So the pKa is the negative of the log of the Ka. Right? In general, the P whatever is the negative of the log of whatever. So the negative of the log of the Ka, this has less meaning. It's not intuitive anymore, but it's a lot easier to use. So anytime we are talking about a strong acid, this has a large Ka, but it has a small pKa. Whenever we're talking about a weak acid, this has a small Ka, but a large pKa. Now you might be used to pKa values, thinking about the pH scale of about 0 to 14, but we can have numbers that are smaller than that and bigger than that. So there are some acids that have pKa's of -4, -6, -10. And then there are some very weak acids that have pKa's in the 20s or 40s or even in the 60s. So it's important to keep in mind when we are talking about a small pKa, then that is a strong acid. A large pKa, that is a weaker acid. Now this table is taken from your book. This is table 2.3, and then this is available in the appendix. And what we're looking at is a variety of pKa values. So for example, here we have ethanol, which has a pKa of 16. This is the conjugate base. So after the acid gave up a proton, what we're left with is the conjugate base. Water has a pKa of 15.7. The conjugate base is hydroxide. Acetic acid has a pKa of 4.7, and its conjugate base is the acetate ion. Hydrochloric acid has a pKa of -7, and its conjugate base is Cl-. So as we're getting to smaller and smaller pKa values, we are getting to stronger and stronger acids. In this table, we have a lot more structures, and in some cases, we're looking at a variety of carboxylic acids. We have an example of an alkane, an alkene, benzene. We have an alkyne. We have amines. There's a wide variety of structures that we have in here, and we're going from very low pKa for all of these organic acids to very, very large pKa for these compounds that are very, very weak organic acids. So in many cases, you'll be able to look up a pKa value, and then you can use that information to determine the strength of a particular acid. In some cases, your tables will have the exact compound. In other cases, you won't have that compound available, but you'll have to use your best judgment about a related compound. But what if you don't have a table of pKa values available? Well, in some cases, you can still determine relative acid strength by knowing some of the ways that structure affects acid strength. And that's what we'll be looking at in the next video.